Hi, my name is Matt Holliday and welcome back to my class on programming in Go. So now I'm going to talk about testing. I want to talk a little bit about the things that Go offers to do testing, and then I want to talk a bit about, well, how should testing be done? And what are the sort of the goals of testing and the limitations of testing, particularly the limitations of unit testing. Go has a bunch of neat built-in test tools. Right? They're not as complicated as some of the packages found in other languages, but I have found them to be pretty effective at doing what they do. All right? So the basic thing about it is you create a file with the ending underscore test. That's where your test stuff goes. It'll be used when you do unit testing, for example. It won't be built into your actual program. And within it, you have functions that start with the word test. And we also saw this with benchmarks. In fact, I think we've already seen testing, right? There's been some of that in some of the other segments in the past. I'm just repeating this, right? Anyway, you have functions that start with test, and you run a tool called goTest. And it runs and tells you how long it took. If there are no errors, it'll also print out more. Great. There is the notion of it caches some results, and so if certain things haven't changed, it just won't run them again. There's no point. You can clear that cache. There's a way to do that. Now, there are a lot of ways to do testing, and I think of them as layers of testing. Okay, and I've drawn a red line here because there's the area of what I think is developer testing, and in this segment I'm going to talk mostly about that. Okay, how to use the tools in Go to do developer testing, right? And then there's things above that, system test and performance testing and chaos testing and so on, all right, that isn't. And I've split end-to-end testing. So we can do unit testing, we can do integration tests, we can do some end-to-end tests and things like that at the developer level. And then there's some higher level things that maybe aren't done by developers. And we'll talk about the why of that. Okay. I also want to suggest you some goals for the testing at the developer level, the kinds of things, right? And the most typical thing, for example, is, well, yeah, look for things like boundary conditions. It's easy to have, my algorithm is supposed to handle numbers from 1 to 1,000. Well, 2, 3, 4 are easy. 0, 1, 999, 1,000, 1001 are the boundary conditions. Okay? Or you can think of those as extreme values, right? Checking your input validation, how do you handle errors, deliberately creating errors. So we also tend to talk about another dimension here. And I'm going to use these terms transparent and opaque. But some people will also talk about white box and black box, right? But transparent tests are the ones where you know something about the software and you're writing unit tests, for example. You really know something about the software. As opposed to testing the system from the outside as a whole system, you don't think about how it's structured. That's not a point. You're just testing the behavior from the outside. So that's a level you can think about. Right? And of course, developer testing, we really want that stuff for sure to be fully automated and baked into our CI/CD process. Okay? There's some other testing that might happen after unit testing, right? Now, fuzz might be part of unit testing, but, deployment testing, right? It's really easy to run through your CI/CD process, deploy something in the cloud, and then have it not work because you had a typo in a config file that you don't know until you actually try to run it in the cloud. So for example, after you deploy, run a little smoke test to say, hey, the thing that I deployed, did it actually wake up and start running properly? Okay. Interface testing, or integration testing. So, I break these things, my boundary, and this may vary for you, between unit tests and integration tests is that unit tests are completely self-contained. They don't need the network, they don't need credentials, they don't talk to another microservice, and they may not talk to a real database unless I can start a database under the control of my UTs, which I do sometimes. Integration tests should test the part of your software that you're not testing UTs, where you actually talk to those other services. Because if you're mocking or faking the other microservices in your UTs, then there's some part of code that's never reached. And the integration tests, which I typically run in CI/CD, actually go out and talk to the development or test versions of other people's microservices to make sure that the credentials are properly inserted, that I can actually properly hook up to those services and actually talk to them. Okay, there's a lot of actuallys in there. All right. So, test functions, right? I already said it's a function starting with test. And here's the simplest version. It's one test in a function. Now I've left out some of the details. But I'm running this one test. It's in isolation. I've got a couple of keys. One of them, there's a teeny weeny difference in the middle of the key. So I'll encrypt with one, and then if I try to decrypt with the other, it won't work or something. Okay? And there's a parameter t. So all of these functions, they take a testing.t pointer, which is something that you can report errors on. Okay? There's the errorf function, okay, or actually in this case, maybe it should have been fatalf. Errorf will report an error and possibly keep going. Fatalf will stop right there. And in a lot of cases, the first thing you do is check to see if things are ready for the rest of your test, so maybe that should be a fatalf. Okay? And there's other things you can do with these. The next level of complexity is, well, it's one test, but I'm going to run it on a range of values. Okay? So this is one way of doing what's called a table-driven test, except in this case, it's just the one test. Right? The table is just a table of values and results. Okay? And then I just have a little loop here that just tries the different values in order and says, hey, this value, that result, does it work? Good as it goes. That's useful. The next thing I'm going to show you is what most people think of when they talk of table-driven tests, and that's table-driven subtests. Okay? Because one of the methods on T is a method t.run. And what it takes is a name and a closure. And it runs that as an individual named subtest. And I'm going to show you in a second. What it changes is how things are reported, how errors are reported, for example. And that can be very useful. To be able to have this thing, once you get your test kind of big, to break it down into subtests so that each subtest can get reported separately. Okay? Now, you know, it's very common in this code to see, here's your table, and maybe the table is an anonymous structure type. There's some values. And then again, you range over here, and you've got this closure right here, which is a function that takes a testing.t pointer. All right, and it takes a name, right? So I have to have a name in my subtest, ideally. All right, and we'll see how this plays out when I run one in a second. Now, what happens with these is they get fairly complicated, right? Particularly if I have an anonymous structure, and then I have a lot of data and so on, okay? And then I've got my closure, and my closure in here starts to get big also, right, with a lot of stuff. And there's a point at which that technique starts to become cumbersome. So I'm going to show you how to refactor this, and I'll show you a couple other things. Let me jump onto my laptop. I want to show you a complicated test out of one of my packages. And what I've done is I've broken it down. So if we look at the bottom part is where I've actually got test the scanner. And what does it do? Well, it goes and runs a range of tests by doing t.run. And so this part's right here. This is the loop. Well, I've broken it out. Okay, the first thing I did is I created a named struct type to actually represent my subtest with whatever data it needs to have. Okay, these are the things that are unique per subtest. And one of the things you're going to want in it is the name, because we give a name to t.run. This is where it comes from. Okay, and then whatever else. In this case, it's like, oh, well, the input that I'm going to provide, which is a string, and the array of tokens that's going to come out of the scanner that I expect to be the result. Great. And I've got that variable down here, right? So if I look at this, I've got a variable, and I'm just going to break it out. It's got the actual test cases, right? Here's one called simple add. It's got my input, and it's got my array of tokens in whatever format happens to be interesting to this program. And there's a bunch of them, right? And again, they take up a bunch of space, which is why I didn't want them all packed into this little function, because that function starts to be unreadable. Now, the other thing I've done is I've created a run method on scanTest. All right? And before I talk about it, and I'm not going to talk about it much, I want to point out when I get down here to the bottom, right, what is st.run? Well, st.run is a method value, right? It's the run method bound to st, which is the particular subtest that I'm seeing each time I go through this loop, right? And what is it? Well, if you look at it, it looks like a func taking a t testing.t, right? That's what it's down to, because that's what's left of the free variables in this method value. So st.run works as a replacement for the closure type that I need to put in here. And here it is. Now, and this is just the logic of my test, right? Take the input, make it into a buffer, create a scanner with it, you know, look at the tokens, and then I'm going to do, in this case, a deep equal, because I need to compare a couple of slices, and they're slices of structs. But it doesn't matter. There are a couple of slices, and you can't do equality on a struct. So this is a great choice of using deep equal in a unit test, and this works just fine. I'm going back to the laptop for a second to show this unit test package in action. Okay, and it turns out VSC, I don't always use this, but VSC has a way to say, like, run the file tests. And if I do that, actually it's going to come back and say they were cached. It would have just said they ran. Okay, that's not very interesting. I want to show the output if I make one fail. So I'm going to come down here and deliberately change one so that it will fail. Run it. Okay, and what's useful here then is to see, right? This is the whole point about the subtests. It says test scanner failed, and it failed in the subtest called test scanner / simple add. Well, that was this first variable I changed right here. I have the simple add subtest, and I just changed one of its values. And of course, down here I have the printout from my stuff, you know, wanted this, got that, right? But what's important is the whole concept of having subtests is it allows you to see these things as names once it starts getting big, and I think that's very valuable. There's another thing I can factor out. I haven't done it in this test because I don't need to. But I have some tests where they start getting big enough that there's a question of, well, how do you decide what a good result is? You know, I've got the values I'm looking for, but how do you check the values? And what I've done in this case is I've created a checker interface, and it takes types appropriate for whatever I'm doing, like in this case 2 strings, right? And the testing.t. And I can create different concrete checkers. Here's an example of, you know, I want a concrete checker that just checks a golden data, right? So it takes these 2 things and looks at the golden data related to this unit test and says, hey, did what I get match the golden data I'm supposed to get, right? But you could conceivably do other things. You could have a checker that would actually take the JSON and decode it and start looking for particular things. Does the JSON sniff right? Okay, so I can actually parameterize my tests, and I can also have some tests where I know they're supposed to fail, right? So I can go ahead and put that in there. And now I run my UT and I look at the results and I say, well, it was marked as it's supposed to fail. Did it actually fail? Right? And if it did fail and is not marked to fail, well, that's an error. And if it's marked to fail and it didn't fail, that's an error. So there's one more thing, and that is, what do I do with complicated things like the database? Okay? If I run against a real database in the cloud, well, that's more of an integration test. I could start some sort of emulator. Okay? If you're using Firestore, Google's Firestore, you could run a Firestore emulator locally and run your unit tests against it. Okay? If you're using Redis, there's a mock Redis package you can actually build into your test program and use it. And then there's actually a great package, I can't remember the guy's name, but it's a way of having your unit test actually start a Docker container with something like Postgres or MySQL. And I think that's still okay, in the sense that the unit test is starting it, it runs, the unit test has to be responsible for taking it down. And as long as your unit test environment has the capacity to do that, great. Okay. Or you can just say, hey, you know what, I've got some UTs where I just want to fake the whole thing out. I'm going to create a dummy little object. And so normally I would say in a Go program, you create interfaces at the consumer point. But the DB is a case where if I want to be able to fake that in my tests, I go ahead and define that right up front. Okay, so I have a DB interface, and then now I can go create a mock DB or fake DB. I use the term mock for a lot of things that in certain cases are probably fakes or something else. I'm not going to worry about it. Okay, I've got a mock DB. Interestingly enough, I can put a fail marker in here. So I can decide for certain UTs to create a database that won't work. Okay, and if it should fail, well then down here in my function, I can just go ahead and return an error that says, yeah, I didn't do that. okay? Or I can have functions that do, and I can just change that by the way I create the mock one test case after another, okay? And now I've just got to implement the actual functions that the database would do down here. And so this is a useful technique. I like for some unit tests to do this, and then when I get to certain more complicated scenarios, I'll use something else. For Redis, for example, it's great that you have an in-memory Redis that you can use in test programs. You can't really do that for something like Postgres. It's just too complicated. I've seen people try it, but they're never really going to have the complete functionality. And trying to chase Postgres and keep up with the changes release after release is going to be painful. Okay, so the other alternative is, and I'm not going to show it here, I'm not ready to show that, is to go down the concept of, having your unit test spin up another process with a Docker container or something to run it. Okay, there's one practice I don't recommend. You could, but I'm not sure I recommend it. And that is, I just write my unit test in the assumption that I have a Postgres instance running on my laptop. You can do that, right? And you got to make sure it's running or your unit tests will all fail. When you get to CI/CD, that may be more difficult. Okay, depends on your CI/CD setup as to whether or not you can set up a database to run that way, or whether you should let your unit tests be responsible for starting it. Okay. There is one more piece that came along, and it's called test main. And this is particularly useful if you need to start up that external emulator. Okay, the test main function will be called first if it exists. And then it's your responsibility to turn around and say, hey, and it takes a testing.m instead of a testing.t. And once you've got things set up, then it's your job to say, okay, now run all the tests and get a result and deal with it. Okay, and that gives you a chance to do something like start the emulator. This is how I do Firestore. I actually have if I'm running locally on my machine, I can actually have a start emulator function that will run the process to run the gcloud command to run Firestore, and then I can work with it and then tear it down at the end. Okay, it's an interesting little exercise in running a command and running a go routine and so on. And other things, right? I could also have the function in here that starts the Redis mock. I've done that. Okay, you're just responsible for doing it and cleaning up. Here, my start emulator function, stop, is a function that returns, right, that I could call. Now, I didn't use defer here, and the reason I didn't use defer is because until recently, the normal way you end your test main is to call os.exit. And if you do that, defer won't run. And there's also certain questions about what happens in a panic. All right, so there's now a slightly different version where if you don't call os.exit, you just return a value from test main, and then somehow it calls os.exit for you. And I haven't tried that to see if you can run defer safely in the test main. Okay, I just don't depend on it. And then there's one more thing, and that is that sometimes you want to test a unit test that sees the package from the outside. Okay, and this is not just the test_test file, it's actually taking your package name and putting an underscore and test at the end of your package name. All right, so when you create a package that has name, and so this is what goes at the top of the file, right? Package x_test alongside, in parallel with some other file that has package x. Okay, the stuff in x_test package, regardless of what file it's in, is not going to be able to use the unexported stuff from X. All right? So that's a good thing. And the other thing it does is it helps break import loops. Now, it's not that well documented, which is why I say go look at Stack Overflow. All right? I don't have the URL handy, but there's a Stack Overflow question that helps explain this. All right? But you're actually looking at package, again, you put an underscore test on the package name. It doesn't get private access to the variables anymore. It's not like a friend, okay? It's just like any other package. It only sees the exported variables. And again, it's also useful to break up import loops. Okay, now I want to completely switch gears. I'm going to stop talking about the mechanics of testing in Go and talk a little bit about testing. All right, because I think there are a few misconceptions about testing and programs. And this is the kind of thing that used to be taught in introductory programming classes like 40 years ago, and it's not really talked about much now, and that's unfortunate. So I'm going to take this opportunity to talk about it. Now, I want to bring another Dave Cheney quote, all right? It's a good thing I don't have to pay Dave Cheney royalties. But this notion of the tests are a contract, and I think that's good, okay? There's going to be some limits to it, but I think it's good, right? You have a package and you have the unit tests of your package. And the unit tests are a type of regression test. Okay, they're also a type of documentation. They help document what the package should do. Now, that documentation is not always easy to read. Okay, so I'm going to argue it's not enough, but it's important that you think about it this way. All right, it's also a very scary thing if you go to some software package, you make a deliberate bug in it, and then you run your UTs and they don't work. Oops. They don't fail, I should say, right? You want and put a bug in it and the UTs don't fail. That tells you the UTs don't work or you don't have enough coverage. So here's the biggest single point I want to make first, okay? As a developer, you should make an assumption about your code. It doesn't work, okay? Now, I could say that just in general. You'll never get all the bugs out. But I mean very specifically, you should assume it doesn't work unless you're testing it, right? You have tests. They actually are functional. In other words, the tests will fail if they should, and they'll work when they should. And you run them, and they all pass. And they all pass because you ran all of them. Okay, I had a coworker once who liked to modify a little piece of the software and run some unit tests associated with that little piece, thinking, well, I know the effect of my change, and I just need to run the subset of the unit tests. And on a regular basis, other parts of the software got impacted. Okay, what does that say? It says it's very hard sometimes to predict what the ripple effect of your change is. So you know what? When you make a change, just run all of the unit tests. Okay. Your work isn't done. Okay. Now, there's this phrase that's sometimes used in the agile process, done, which I hate because it suggests that when you said you were done, you weren't. Oh, so are you really done? Okay. Yeah. Well, you're not done unless you've added or updated the tests to reflect the changes you made to the software. And then also run them and make sure they all work. Okay? And nobody should ever have to write that into your ticket as a particular task. That's just the assumption. If you've done a ticket to change software, you've also fixed the tests and run them. Okay? And this is back to my philosophy of start clean, stay clean. Right? Now, if you're doing TDD, or particularly like an orthodox implementation of TDD, then this is sort of a no-brainer. Okay? I don't always do that. I like TDD, but I don't necessarily do it in a religious fashion. Now, there's another factor going on here, and this gets to more of, the testing and the limits of unit testing. All right? There's this quote here about the mental model. And mental model is important. So I always say imagination is important for a developer because so much of it takes place in your head. Okay? Yeah, you could print out your code and look at the piece of paper, or maybe look at it on the screen and call that an artifact. But so much of what happens in software development happens in your head. What happens as developers is we get focused in. We look at this thing with blinders, the thing we're working on, that we know this is what it is and what it's supposed to do. All right? And by getting focused in like that, we miss things. Almost all serious problems in software now really come down to a failure of the imagination. All right? Let me jokingly say this, right? That the post-mortem is going to be somebody saying, well, I never thought they would push that button. All right? That's the kind of thing I mean by failure of the imagination. And we get there because we get locked in as developers. Developers test to show that things work, to show that the work has been done. And again, if you're talking about TDD, that's the whole point of TDD. Okay, great. It's not enough. Okay? When we talk about program correctness, and this is literally something I've lifted out of a textbook from the 70s. Again, you don't see this stuff in textbooks today, like introductory programming textbooks. That's very unfortunate. Okay? What does it mean for a program to be right? In some, right with quote marks on it. Okay? Here are 8 levels of correctness. Right? From I got it to compile to it just works. All right? Now, I'm going to say a couple things. First, the only goal you should ever have is level 8. It just works. By works, we mean, hey, it either does what it's supposed to do or it fails in some intended safe way. Maybe it just stops and prints out an error message, okay, or it crashes or something. It fails safely, or it does what it's supposed to do. That's the goal. Now, I'm also going to say that when you get down to the bottom levels of this, you can't get there by empirical testing. There's no amount of testing that will show a program has no bugs. And we've known that about as long as I've been alive. Okay? There are some techniques, though, for fuzz testing, for example, is great, because fuzz testing allows you to try a couple of these things probabilistically. All right? We'll generate a bunch of random junk and see what happens. So we may not be able to test everything. The problem with testing these bottom levels like 8 is the amount of input is infinite in almost any program. Okay? Fuzz testing, chaos testing at a system level, again, those are great ways to try to hit those higher levels of correctness. But this is a way of thinking, well, what are you testing for? Because you may look at this and say, well, yeah, you know, I only get to like 4 or 5. All right? And that's where a lot of people get to. Okay? And you got to go past that. You got to go try to go past that. All right? That's one side of the picture. The other picture, and again, it's from the same textbook, right, is where do the errors come from? Okay, well, you didn't understand what it's supposed to do, or you didn't understand your language. Thankfully, Go is easy. That helps on that part. Or you didn't understand your program, the logic or the algorithm of your program. Or you just made a dumb mistake. Okay, you know, I'm going to tell you that some of these things, they get better with experience, right? The experienced developer should make less of these until you get to number 4, and then it just doesn't matter. I don't care how many years you've been programming. I've been doing it for 45. I still make dumb mistakes. All right? It happens. That's why we have code reviews and testing. So, what's interesting is this comment, you know, type 1 errors, and this is from the book, well, they tend to get bigger as these programs get bigger and more complicated. And as the information about, well, what do we think it should do becomes less specific. All right? So I've turned that into a little chart. On the left-hand side of this are what I call implementation problems, bugs. All right? On the right, requirements. In other words, what do we think it's supposed to do? Right? Obviously, we have requirements sometimes that are just wrong. They've been written down wrong. Or what happens a lot is, well, the person who wrote the requirements has this one idea in mind, and the people reading them read it differently. So misunderstood requirements is a good source of errors. A lot of errors get traced back to that. Okay, I could drill down to that more, but I won't today. And on the left-hand side, again, we've got these things about, you know, the high level, the mid-level, the low-level logic, all right? And this category of, you know, dumb mistakes that just happen. And then there's the interesting thing going on here, right? The requirements that are missing, and on the lower left, the code that is missing. All right? Now, the code could be missing for any of the reasons on the right. You know, we don't have a requirement to write the code, or we misunderstood the requirements. So there's not necessarily a direct tie across here, although there could be. Okay, right? And although this is not to scale, I have made this section on missing requirements bigger because I think that's the biggest single problem. Right? We're writing software without a good, clear understanding of what we think it should do. Right. So, where does that get us? Right? I think developer testing is necessary. All right? I mean, there's this question of, well, should developers test and how much? You know, and it used to be in the past, developers did very little testing. They just took the stuff and threw it, as they say, over the wall to the testers. And the testers would get crap that doesn't even run to start with. All right? And I think that's a very, very bad process. It's disrespectful of the testers. Now, it's fair to say, for most of my career, developers have been like the top level people and the testers have been lower down on the status ladder, right? And we all know that the stuff flows downhill, and so it flows downhill on testers. And again, I think that's awful. I think that's a big mistake, okay? Anyway, developer testing is a good thing, right? Unit tests, integration tests, post-deployment sanity tests, and from that we get code coverage. And there's been a fetish about code coverage. I think code coverage is good. And in another segment, I'm going to show you how Go has tools to help you look at the code coverage. We're going to work through an exercise, okay? You know, the number should be fairly high, 75, 85%. I don't think that's very challenging, all right? Some people will say it should be 100%. And the difficulty is, you know, to get to the 100%, you're going to have to do some really weird things in your code, which might make it worse, okay? And the other thing I'm going to say is the 100% number gives you a false sense of security. Okay? But I do think, yeah, developers must be responsible for the quality of the code. So the stuff that you commit, the stuff that you merge, okay, the stuff you deploy should be good. Your intention should be well, maybe not every commit to your development branch, but everything you deploy to a common branch, or to the final release branch, or however you manage your software, right? Certainly anything you deploy into production and probably into staging, your intention should be, this is 100% good. Okay, you won't get there, but that should be your intention. Right. And as I said with the quote from Dave Cheney, testing can be part of your documentation. Okay, there's a problem that I think it's worth drilling down because I find this problem in a lot of organizations. It's a fundamental misunderstanding about what testing is. And it's this horrible term QA. So I'm going to tell you, having managed QA, that QA is not what you think it is. It's not testing. QA is the process of managing the actual quality process overall that sits over development and test and software support and whatever. All the activities are under the umbrella of QA, right? It's not testing. But bringing a QA mentality that comes out of manufacturing where, I've got this assembly line, it makes left-handed green widgets, and I want to take one and see if it matches the specification. Is it made within the tolerances that the specification says it's supposed to have? Okay, statistical quality control. Great, but it doesn't apply to software because software is not manufacturing. Okay, and the other thing is, here's the real killer. Okay, the notion of, well, I'm just checking to see that it works. That's, I think, for a test perspective, not valuable. Developers are going to test to show it works, and they should be doing that. Okay, and they should have enough tests to show that the happy path works before they hand it off to anybody else. Okay, but for the testers to go down there and just say, well, I'm just checking the happy path, is very unsatisfactory. Okay, it is a problem that's actually been documented. It's the wrong testing mindset, and it leads to inadequate testing because the function of testing is to find defects by breaking the system. That's the only function of testing. Testing is not about showing that it works. It's about showing that it doesn't. Okay? And that's why I'm going to say developer testing is not enough. This is a sales pitch. And I've seen organizations that don't have any testing other than the developers. And I've also seen one of those organizations where problems got to the point where some high-level executive said, well, do you just not test your software? And I would have loved to have been a fly on the wall in the room when that conversation was being had. Okay? So you can be 100% code coverage from a developer testing perspective and be wrong because the requirements are wrong, or you misunderstood the requirements, or, hey, if you didn't write the code, you can't cover it. Okay, so I said again, the function of test is to show that things don't work. The mindset of a tester is separate from a developer. Okay, so there's two things about having a separate test function. One, they're not trapped by these blinders about, oh, this is what it is. Because the developer gets focused in, this is what it is, and the tester's the guy who comes along and says, well, this is what it isn't. All right? So they're independent in the sense they're not locked into a certain vision of it, and they come from a different angle. They're intending to show that it's broken. And the more they can break it, the better, because that's what's going to surface or expose the defects so they can get fixed. Okay? And I'm going to say a couple more words, just a little bit, while I'm up on this soapbox. Okay? It's hard to do testing when there's no documentation. Now, most people now develop in an agile process. And if you go back to the Agile Manifesto, it will say something like, prefer working software to documentation, which is fine. Unfortunately, many people practice Agile as if it said, well, just write the software and don't bother documenting it. It doesn't say that at all. Okay? Documentation is necessary, and while the unit test can help document, it's not enough. Okay? If I look at the major sources of technical debt in most of the stuff I've worked on, it's some combination of not enough testing and not enough documentation. And nobody likes writing documentation, but it's necessary. All right. So I want to finish up with, there's this old engineering notion. Good, fast, cheap, pick any two. And there will always be some software development manager walk along and say, no, that's not true. I can have them all. No, they can't. Okay. If testing is inadequate, it's usually because people don't want to pay for it. And if you're not happy with the way it works, then you need to be a change agent and manage up and help explain the value of testing. Okay. I find modern software very annoying because it kind of works except when it doesn't. And it kind of works except when it doesn't because most of the people building the software that I end up using, okay, are focused on the fast and the cheap and not the good. Okay, so that's my explanation of testing in Go, and then my little soapbox speech about what is testing and what isn't it and why should you do it. All right. If our goal is quality software, then testing has to be part of that. We want to use the tools as much as possible to test the code at the developer level, and then recognize that we need another level of testing from a different direction with a different goal to help find the rest of the bugs that the developers don't see because they just can't imagine they're there.